Welcome to the fascinating world of sequences and series. These fundamental mathematical concepts appear everywhere around us, from the patterns in nature to complex financial calculations. In this comprehensive study, we will explore two main types of mathematical patterns: sequences and series. Let's begin by understanding what makes each of these concepts unique and powerful. A sequence is simply an ordered list of numbers that follow a specific pattern or rule. For example, the numbers 2, 4, 6, 8, 10 form a sequence where each number increases by 2. Now let's explore series, which are closely related to sequences but serve a different mathematical purpose. A series takes those same sequence numbers and adds them together. So our sequence 2, 4, 6, 8, 10 becomes the series 2 plus 4 plus 6 plus 8 plus 10, which equals 30. Throughout this course, we'll focus on two special types of sequences and series that have unique properties and widespread applications. We'll study arithmetic sequences, where there's a constant difference between consecutive terms, and geometric sequences, where there's a constant ratio between consecutive terms. These mathematical concepts aren't just abstract ideas. They have practical applications in many fields that affect our daily lives. You'll find sequences and series in finance for calculating loan payments and investment growth, in physics for understanding wave patterns and decay processes, and in technology for developing algorithms and analyzing data. As we progress through this grade 12 level content, you'll develop the skills to recognize patterns, solve complex problems, and apply these concepts to real-world situations. Let's begin this mathematical journey together. A sequence is simply an ordered list of numbers. Think of it like a line of people waiting. Each person has a specific position, and the order matters. Let's look at a simple example. Here we have the sequence 2, 4, 6, 8. Each number is called a term, and they follow a specific order. Each number in a sequence is called a term. We use subscript notation to identify the position of each term. The first term is A1, the second term is A2, and so on. This subscript notation is standard in mathematics. Let's see how this looks in a more formal mathematical context. Sequences can follow many different patterns. Here's a beautiful example of triangular numbers, where each term represents the sum of consecutive integers starting from 1. Remember the key points. A sequence is an ordered list of numbers. Each number is called a term, and we use subscript notation like A1, A2, A3 to identify the position of each term. An arithmetic sequence is a special type of sequence where something very important stays the same between consecutive terms. The key characteristic of an arithmetic sequence is that the difference between consecutive terms is always constant. This means we add or subtract the same number each time we move from one term to the next. This constant difference has a special name. We call it the common difference, and we represent it with the letter D. Let's look at some visual examples to understand this better. Here we can see two different arithmetic sequences side by side. On the left side, we see an increasing arithmetic sequence where each term gets larger by adding positive 4. On the right side, we have a decreasing arithmetic sequence where each term gets smaller by subtracting 3, which is the same as adding negative 3. Here's another way to visualize arithmetic sequences using a number line. We can see how adding or subtracting the same amount creates a pattern. The arrows show us the direction and size of the common difference. Moving right with +1 creates an increasing sequence, while moving left with -1 creates a decreasing sequence. Let's create our own simple example. Consider the sequence 1, 3, 5, 7, and so on. What do you notice about the differences between consecutive terms? Let's calculate the differences. From 1 to 3, we add 2. From 3 to 5, we add 2. From 5 to 7, we add 2. The common difference is 2, making this an arithmetic sequence. So we can say that this arithmetic sequence has a common difference of D equals 2. Every term is exactly 2 more than the previous term, creating a predictable pattern. Understanding this concept of common difference is fundamental to working with arithmetic sequences, as it allows us to identify patterns and make predictions about future terms. The common difference is the key characteristic that defines an arithmetic sequence. It's the constant value that we add to each term to get the next term in the sequence. To find the common difference, we use a simple formula. We subtract any term from the term that follows it. This gives us d equals a sub 2 minus a sub 1, which equals a sub 3 minus a sub 2, and so on. Let's see this in action with some examples. Here we have two different arithmetic sequences, one that increases and one that decreases. Notice how each sequence has its own constant difference. For the increasing sequence on the left, let's calculate the common difference. We take 9 minus 5, which equals positive 4. We can verify this by checking 13 minus 9, which also equals 4. The common difference is positive 4. Now for the decreasing sequence on the right, let's calculate 17 minus 20 equals negative 3. We can verify with 14 minus 17, which also equals negative 3. The common difference is negative 3, showing that the sequence decreases by 3 each time. The key insight is that the common difference remains constant throughout the entire arithmetic sequence. Whether positive or negative, this value never changes, which is what makes the sequence arithmetic. You can calculate it using any two consecutive terms and get the same result. The general term formula is the key to unlocking any arithmetic sequence. Instead of writing out every single term, we can use one powerful formula to find any term we want. This formula has 4 important components, each with a specific meaning. Let's break down what each variable represents in our arithmetic sequence formula. Let's see this formula in action with a concrete example. Here we have an arithmetic sequence where each term decreases by 4. Notice how the common difference is negative 4. Now let's apply our formula to this sequence. The first term, a1, is 21, the common difference d is negative 4, and we can find any term n using our general formula. The power of this formula becomes clear when we want to find a term far into the sequence. For example, what's the 50th term? Without the formula, we'd have to write out 49 terms. With the formula, it's just one calculation. This formula works for any arithmetic sequence, whether the common difference is positive or negative, large or small. It's a universal tool that makes working with arithmetic sequences efficient and precise. Let's work through a specific example of finding a term in an arithmetic sequence. We have an arithmetic sequence where the first term is 3, the common difference is 4, and we want to find the 10th term. We'll use the arithmetic sequence formula to solve this problem. The formula states that the nth term equals the first term plus the common difference times n minus 1. Now let's substitute our values into the formula step by step. Step 1, we start with the general formula for the nth term. Step 2, we substitute our known values. A equals 3, d equals 4, and n equals 10. Step 3, we simplify inside the parentheses. 10 minus 1 equals 9. Step 4, we multiply 4 times 9 to get 36. Step 5, finally, we add 3 plus 36 to get our answer. The 10th term of this arithmetic sequence is 39. Let's visualize this sequence to better understand our result. Here we can see the first 5 terms of our sequence: 3, 7, 11, 15, and 19. Each term increases by 4, which is our common difference. Following this pattern all the way to the 10th position, we arrive at our calculated answer of 39. In this example, we'll learn how to find the common difference when we know 2 specific terms of an arithmetic sequence. We're given that the third term of an arithmetic sequence is 7, and the 7th term is 15. Our goal is to find the common difference d. We'll use the general formula for arithmetic sequences to set up our equations. Recall that the nth term equals the first term plus n minus 1 times the common difference. Now let's set up our 2 equations using the given information. For the third term, we substitute n equals 3 into our formula. This gives us a sub 3 equals a sub 1 plus 2d, which equals 7. Similarly, for the 7th term, we get a sub 7 equals a sub 1 plus 6d, which equals 15. Now we have a system of 2 linear equations with 2 unknowns that we need to solve. Let's solve this system step by step using the elimination method. We'll use elimination to solve this system. Let's subtract the first equation from the second equation. Rearranging the terms, we get 8 equals 4d. Dividing both sides by 4, we find that d equals 2. Now let's find the first term by substituting d equals 2 back into one of our original equations. Substituting d equals 2 into our first equation, we get 7 equals a sub 1 plus 4, so a sub 1 equals 3. Therefore, our arithmetic sequence has a first term of 3 and a common difference of 2. We can verify this is correct by checking that the third term is 3 plus 2 times 2, which equals 7, and the seventh term is 3 plus 6 times 2, which equals 15. A geometric sequence is a special type of sequence where each term is found by multiplying the previous term by the same constant value. This means that to get from one term to the next, we always multiply by the same number. This constant multiplier is called the common ratio. We call this constant multiplier the common ratio, and we usually represent it with the letter r. Let's look at a concrete example. Consider the sequence 2, 4, 8, 16, 32. Notice that each term is exactly double the previous term. Since we multiply by 2 to get each new term, the common ratio r equals 2. Here are two more examples of geometric sequences. The first sequence shows each term multiplied by 2, while the second shows each term divided by 2, which is the same as multiplying by 1/2. Mathematically, we can find the common ratio by dividing any term by the previous term. This gives us a consistent value throughout the sequence. This constant ratio is what makes the sequence geometric. No matter which consecutive terms we choose, we always get the same ratio value. Geometric sequences appear naturally in many visual patterns. These geometric shapes demonstrate how quantities can grow or shrink by constant ratios, creating beautiful mathematical patterns. To summarize, geometric sequences have a constant ratio between consecutive terms. Each term equals the previous term multiplied by r, creating the pattern AR, r squared, r cubed, and so on. To find the common ratio in a geometric sequence, we need to understand what makes these sequences special. The common ratio is the constant value we multiply or divide by to get from one term to the next. The formula for finding the common ratio is straightforward. We divide any term by the term that comes before it. This gives us r equals a sub 2 divided by a sub 1, which equals a sub 3 divided by a sub 2, and so on. Here's a concrete example. We have the geometric sequence 256, 64, 16, 4, and so on. To find the common ratio, we divide the second term by the first term. 64 divided by 256 equals 1/4. Let's work through this step by step. First, we choose any two consecutive terms. Here we'll use 64 and 256. Next, we simplify the fraction. 64 divided by 256 equals 1 divided by 4, or 1/4. To verify our answer, we can check with other consecutive terms. 16 divided by 64 also equals 1/4, and 4 divided by 16 also equals 1/4. This confirms that our common ratio is correct. The most important thing to remember is that the common ratio remains constant throughout the entire geometric sequence. No matter which consecutive terms you choose to divide, you will always get the same ratio value. We have a geometric sequence where the first term is 5 and the common ratio is 3. Our goal is to find the sixth term of this sequence. We'll use the general formula for geometric sequences. The nth term equals the first term multiplied by the common ratio raised to the power of n minus 1. Now let's substitute our values into the formula and calculate step by step. Step 1, we substitute a1 equals 5, r equals 3, and n equals 6 into our formula. Step 2, we simplify the exponent. 6 minus 1 equals 5, so we have 5 times 3 to the 5th power. Step 3, we calculate 3 to the 5th power. 3 times 3 times 3 times 3 times 3 equals 243. Step 4. Finally, we multiply 5 times 243 to get 1215. Therefore, the sixth term of our geometric sequence is 1215. This demonstrates how we can find any term in a geometric sequence using the general formula. In this example, we'll find the common ratio of a geometric sequence when we know specific terms but not the first term. We're given that the second term equals 6, and the fifth term equals 48. First, we'll set up equations using the general term formula. The second term is a1 times r to the first power, which equals 6. The fifth term is a1 times r to the fourth power, which equals 48. Here's the key insight. If we divide the second equation by the first equation, the a terms will cancel out, leaving us with an equation that only contains r. Let's perform the division. We divide a1 times r to the fourth power equals 48 by a1 times r equals 6. This gives us r to the third power equals 48 divided by 6. Now we simplify. The A1 terms cancel out, and r to the fourth power divided by r equals r to the third power. So we have r cubed equals 8. To find r, we take the cube root of both sides. The cube root of 8 is 2, so our common ratio is 2. Let's verify our answer by checking if it works with our original information. If r equals 2, then we can find the first term and check our work. Now we can check the fifth term. With a1 equals 3 and r equals 2, the fifth term should be 3 times 2 to the fourth power, which equals 3 times 16, which equals 48. This matches our given information, confirming our answer is correct. The complete geometric sequence starts with 3, then 6, 12, 24, 48, and continues with each term being multiplied by our common ratio of 2. Now that we understand sequences, we can explore what happens when we add up the terms of a sequence. This leads us to the concept of a series. A series is formed when we add up the terms of a sequence. Instead of just listing the terms, we combine them with addition signs. The result of adding all these terms gives us the sum of the series. In this case, 2 plus 4 plus 6 plus 8 plus 10 equals 30. To represent series mathematically, we use a special symbol called the summation symbol. This is the Greek letter sigma, written as a large. It tells us to add up a series of terms according to a specific pattern. Series can be classified into two main types, finite series and infinite series. An infinite series continues forever, indicated by the 3 dots at the end. Whether a series is finite or infinite affects how we calculate its sum. Let's look at a concrete example of how we work with series using summation notation. This example shows how we can find the sum of a finite geometric series. Notice how the summation symbol organizes the calculation, making it clear what terms to add and how many terms are included. Understanding series is crucial because they appear everywhere in mathematics, from calculating compound interest to analyzing patterns in nature. The summation symbol provides us with a powerful tool to work with these mathematical concepts efficiently. Now that we understand arithmetic sequences, we can explore arithmetic series. An arithmetic series is simply the sum of the terms in an arithmetic sequence. An arithmetic series takes these sequence terms and adds them together. Instead of just listing the terms, we find their sum. For any arithmetic series, we have two useful formulas to find the sum of the first n terms. Let me show you both formulas. The first formula uses the first term and the last term. S sub n equals n over 2 times the quantity a sub 1 plus a sub n. The second formula uses the first term and the common difference. S sub n equals n over 2 times the quantity times a sub 1 plus n minus 1 times d. Let me explain what each variable represents in these formulas. This will help you choose which formula to use in different situations. Both formulas will give you the same result. Use the first formula when you know the first and last terms. Use the second formula when you know the first term and common difference. A geometric series is the sum of the terms in a geometric sequence. While a sequence lists terms in order, a series adds them together. When we add these terms together, we get a geometric series. Instead of listing the terms, we're finding their sum. The sum of the first n terms of a geometric series has a specific formula. This formula allows us to calculate the total without adding each term individually. Let's break down each component of this formula. S sub n represents the sum of the first n terms. A sub 1 is the first term of the sequence. There's an important restriction. This formula only works when r is not equal to 1. When r equals 1, all terms are the same, and we use a different approach. This formula is incredibly useful because it gives us the exact sum without having to add each term manually, especially when dealing with many terms. Understanding this formula is key to working with geometric series efficiently. In the next section, we'll see how to apply this formula with specific examples. Now let's work through a concrete example of calculating a geometric series. We'll take a specific geometric sequence and find the sum of its first few terms. Consider this geometric sequence, 3, 6, 12, 24, and so on. Our goal is to find the sum of the first 4 terms of this sequence. First, we need to identify the key components of our geometric series. The first term, n equals 3, the common ratio r equals 2, and we want the sum of n equals 4 terms. Now we'll apply the geometric series formula. The formula for the sum of the first n terms of a geometric series is Sn equals a1 times 1 minus r to the n, all divided by 1 minus r. Let's work through this step by step. First, we calculate 2 to the fourth power, which equals 16. So we have 3 times 1 minus 16 divided by 1 minus 2. Next, we simplify the numerator and denominator. 1 minus 16 equals negative 15, and 1 minus 2 equals negative 1. Now we can simplify the fraction. Negative 15 divided by negative 1 equals positive 15. So we have 3 times 15. Finally, we multiply 3 times 15 to get our answer, 45. Therefore, the sum of the first 4 terms of the geometric sequence 3, 6, 12, 24 is 45. An infinite geometric series extends a geometric series to have infinitely many terms. Unlike finite series, we need special conditions for these infinite series to have a meaningful sum. The key question is, when does an infinite geometric series converge to a finite sum? The answer depends on the common ratio r. Let's visualize why this condition matters. When the absolute value of r is less than 1, each term becomes smaller and smaller, allowing the series to approach a finite sum. When this convergence condition is met, we can calculate the exact sum using a beautiful formula. Let me show you the formula for the sum of an infinite geometric series. Let's examine a concrete example to see how this works in practice. Consider the series 3 plus 1 plus 1/3 plus 1/9, and so on. In this example, we can see that the first term a equals 3, and the common ratio r equals 1/3. Since the absolute value of 1/3 is less than 1, this series converges. Now we can apply our formula to find the exact sum. Using s equals a1 divided by 1 minus r, we get s equals 3 divided by 1 minus 1/3, which equals 3 divided by 2/3, giving us a final sum of 4.5. This means that if we could add up all infinitely many terms of this series, the total would be exactly 4.5. This is the power of infinite geometric series. They can converge to precise, finite values. Now we'll work through a specific example of calculating an infinite geometric series. This will demonstrate how to apply the convergence formula in practice. First, we identify the key components of this geometric sequence. The first term a equals 1, and we can find the common ratio by dividing any term by the previous term. Next, we must check the convergence condition. For an infinite geometric series to have a finite sum, the absolute value of the common ratio must be less than 1. Since the convergence condition is satisfied, we can apply the infinite geometric series formula. The sum equals a1 divided by 1 minus r. Now we substitute our values step by step. S equals 1 divided by 1 minus 1/2, which simplifies to 1 divided by 1/2, giving us a final answer of 2. Let's visualize what this means. The image shows how each term in the series gets progressively smaller, and they all add up to exactly 2. This example demonstrates the power of infinite geometric series. Even though we're adding infinitely many terms, the sum converges to the finite value of 2, showing how mathematical infinity can yield concrete, calculable results. Arithmetic and geometric sequences aren't just mathematical concepts. They have powerful applications in real-world scenarios. Let's explore how these sequences help us model and solve practical problems. Arithmetic sequences are perfect for modeling situations with constant increases or decreases. One of the most common applications is simple interest calculations. In simple interest, the interest earned each year remains constant. This creates an arithmetic sequence where each term increases by the same amount, the annual interest payment. Notice how the interest earned each year is exactly the same, £100. This constant difference makes it an arithmetic sequence with a common difference of 100. Geometric sequences model exponential growth and decay. The most familiar example is compound interest, where your money grows by a constant percentage each period. The compound interest formula shows how your investment grows geometrically. Each period, your balance is multiplied by the same growth factor, creating a geometric sequence. Unlike simple interest, compound interest grows exponentially because you earn interest on your interest. This multiplication by a constant ratio is the hallmark of geometric sequences. Another powerful application of geometric sequences is modeling population growth. When populations grow at a constant percentage rate, they follow geometric patterns. This graph compares exponential growth, which follows a geometric sequence, with logistic growth that eventually levels off. Pure exponential growth assumes unlimited resources and constant growth rates. In reality, most populations eventually face resource constraints, leading to logistic growth. However, geometric sequences perfectly model the initial exponential phase of population growth. To summarize, arithmetic sequences model constant changes like simple interest and regular salary increases, while geometric sequences capture exponential phenomena like compound interest and population growth. Understanding these patterns helps us analyze and predict real-world situations. When working with sequences and series problems, following a systematic approach will help you solve them accurately and efficiently. Here are the essential problem-solving tips you need to master. The first and most crucial step is identifying whether you're dealing with an arithmetic or geometric sequence. Look at the pattern between consecutive terms. If there's a constant difference, it's arithmetic. If there's a constant ratio, it's geometric. Always write down all the given information clearly. This includes the first term, the common difference or ratio, the term number you're looking for, and any other given terms. Having everything organized prevents mistakes and makes the solution process smoother. Once you've identified the sequence type, choose the correct formula. For arithmetic sequences, use an equals a1 plus n minus 1 times d. For geometric sequences, use an equals as1 times r to the power of n minus 1. These examples show both formulas in action. Follow this systematic approach for every problem. Start by reading carefully, identify the sequence type, organize your information, choose the right formula, substitute values correctly, calculate step by step, and always check your final answer. Finally, always double-check your work. Verify that your answer makes sense in the context of the problem, confirm you use the correct formula, check your arithmetic, and ensure the pattern continues as expected. This final step prevents most common errors. By following these systematic problem-solving tips, you'll approach sequence and series problems with confidence and accuracy. Remember, identify, organize, choose, substitute, calculate, and check. When working with sequences and series, there are several common mistakes that students frequently make. Understanding these pitfalls will help you avoid them and solve problems more accurately. The first common mistake is confusing arithmetic and geometric sequences. Students often see a sequence like 2, 5, 8, 11 and mistakenly think it involves multiplication when it actually involves addition of a constant difference. Another frequent mistake is using the wrong formula for series. Students sometimes use the geometric series formula when they need the arithmetic series formula, or vice versa. Always identify the sequence type first. A critical mistake with infinite geometric series is ignoring the convergence condition. The series only has a finite sum when the absolute value of the common ratio is less than 1. If this condition isn't met, the formula doesn't apply. Finally, many students make careless substitution errors. They might forget to use n minus 1 in the arithmetic sequence formula or make simple arithmetic mistakes. Always substitute values step by step and double-check your work. By being aware of these common mistakes and taking care to identify sequence types, use correct formulas, check convergence conditions, and substitute values accurately, you'll significantly improve your success with sequences and series problems. We've reached the end of our comprehensive journey through sequences and series. This conclusion will help you consolidate your learning and discover exciting paths for further mathematical exploration. Throughout this series, we explored 5 key areas. We learned about arithmetic sequences with their constant differences, geometric sequences with their constant ratios, how to sum these sequences into series, real-world applications, and essential problem-solving strategies. The key to mastering sequences and series is consistent practice. Work through various problems, from basic pattern recognition to complex real-world applications. Each problem you solve strengthens your mathematical intuition and problem-solving skills. Ready for more advanced topics? Consider exploring recursive sequences where each term depends on previous terms, sequences in calculus including limits and convergence, advanced series like power series and Fourier series, and mathematical modeling using sequences in fields like finance, biology, and physics. Thank you for joining me on this mathematical journey through sequences and series. Remember, mathematics is a language that describes patterns in our world. Keep practicing, stay curious, and continue exploring the beautiful connections between numbers, patterns, and real-world phenomena. Your mathematical adventure is just beginning.